For the last few years, the entire conversation around AI progress has been about one thing: more compute. More GPUs, bigger data centers, more electricity, more raw processing power crammed into ever larger clusters of chips working together. But on July 13, 2026, researchers at Peking University published a paper suggesting that the real bottleneck holding AI back was never really about how fast any individual chip could calculate. It was about how slowly those chips could talk to each other. Their solution was almost deceptively simple to describe. Instead of sending data between chips through traditional electrical wiring, the way essentially every computer on Earth currently does, they connected standard, ordinary electronic AI chips using beams of light instead. The result? Distributed AI inference speeds boosted by more than 100 times, while using just 1/9 of the typical computational resources needed to do the same job. Not 100% faster, 100 times faster, using 9 times less compute at the same time. If that number holds up as this technology scales, it could change one of the most expensive, most talked about constraints in the entire AI industry. So what exactly did they build? And why does something as old and simple as light solve a problem that more powerful chips alone never could? Let's break it down.
To understand why this matters, you need to understand what actually happens when a large AI model answers your question. Modern AI systems, especially the largest models capable of complex reasoning, are far too big to run on a single chip. Instead, the workload gets split across dozens, sometimes thousands of GPUs working together in parallel, constantly passing pieces of data back and forth as they process a request. This is called distributed inference, and it depends entirely on how quickly those chips can communicate with one another, not just on how powerful any single chip is individually. Here is the problem. Traditional electrical connections between chips, the copper wiring and circuit board pathways that carry data as electrical signals, have a hard physical ceiling on how much information they can move per second, and how much energy that movement costs. As AI models have grown larger and more complex, this communication overhead has quietly become one of the largest hidden costs in running modern AI at scale, alongside the electricity spent on raw computation itself. The industry's usual answer has been to simply add more GPUs to spread the workload further, but that approach runs into rapidly diminishing returns because every additional chip added to the cluster also adds more communication overhead between chips, not just more computing power. At some point, adding more chips stops making the system meaningfully faster and just makes it more expensive to run.
The research, published in the journal National Science Review, was led by corresponding authors Xu Wen and Wang Xingjun at Peking University. Rather than designing an entirely new type of computing chip, the way some previous Chinese chip research has focused on, all-optical processors that compute using photons directly, this team took a different, more immediately practical approach. They kept standard, conventional electronic AI chips exactly as they are, and instead replaced the connections between those chips with an all-optical interconnect system. In simple terms, information leaving one chip gets converted into pulses of light, travels between chips at the speed of light through optical pathways rather than electrical wiring, and then gets converted back into electrical signals once it reaches its destination chip. Paired with specific algorithms designed to take advantage of this optical connection method, the team's system delivered its headline result: over 100 times faster distributed inference speeds, using only about 1/9 of the typical computational resources such a workload would normally require. The genuinely clever part of this approach is that it does not require redesigning the actual computing chips themselves. It solves the communication bottleneck without needing an entirely new generation of processors to be manufactured first.
It helps to understand, at a basic level, why replacing electrical wiring with light actually works so well for this specific problem. Electrical signals traveling through copper wiring lose energy as heat the further they travel and the faster you try to push them, a phenomenon engineers call resistive loss. This is exactly why processors get hot, why cooling systems in data centers are so enormously expensive to run, and why there are hard physical limits on how fast electrical signals can reliably travel between chips without errors creeping in. Light, moving through an optical fiber or waveguide, does not suffer from that same resistive loss in nearly the same way. It can carry enormous amounts of data across relatively long distances, with dramatically less energy wasted as heat along the way. This is not a brand new scientific insight. Fiber optic cables have used exactly this principle to move data around the world for decades, which is why your home internet connection likely runs, at least partly, through fiber optic lines rather than old-fashioned copper telephone wiring. What Peking University's team did was bring that same fundamental advantage down to a much smaller, much more localized scale, connecting individual chips sitting right next to each other inside a single server rack or data center rather than connecting entire cities.
It would be easy to read the headline number here, 100 times faster, and treat it as simply an efficiency upgrade, a nice bonus that makes existing AI systems run a bit cheaper. But the deeper implication is arguably more significant than that. If chip-to-chip communication has quietly become the actual limiting factor in scaling AI systems rather than raw computing power, then solving the communication bottleneck changes the entire calculation around how AI infrastructure gets built going forward. Instead of the industry's default answer to every scaling problem being simply buy more GPUs, an optical interconnect approach like this one suggests systems could achieve dramatically better performance using fewer chips, connected far more efficiently. That has enormous implications for the eye-watering capital costs of building AI data centers, for the equally staggering electricity demands those data centers place on power grids around the world, and potentially for how quickly newer entrants, without access to the largest GPU stockpiles, could compete with better resourced rivals simply by connecting the chips they do have far more intelligently. In an industry where the conversation has been dominated almost entirely by chip export restrictions and GPU stockpiling, a genuine breakthrough in how chips talk to each other is a different kind of lever entirely, one that doesn't depend on getting your hands on more of the same scarce hardware everyone else is fighting over. Some researchers and analysts following this story have pointed to an even more ambitious, longer-term implication buried inside this result. If optical interconnects can reliably link separate, independent chips together at light speed with minimal energy loss, the next logical step is combining hundreds of smaller, cheaper microchips onto a single large wafer, all communicating with each other through this same optical method, effectively functioning as one enormous, unified processor rather than many separate ones. This approach, sometimes described as nano-imprinting individual chips onto a monolithic wafer, could potentially sidestep one of the most expensive and heavily restricted parts of modern chip manufacturing entirely: the need for extreme ultraviolet lithography machines to print ever smaller transistors onto a single piece of silicon. Instead of needing the most advanced, most tightly export-controlled manufacturing equipment on Earth to build one enormous chip, this vision would allow many smaller, more easily manufactured chips, connected optically, to behave collectively like one much larger and more powerful system. That is still a longer-term vision, rather than something demonstrated at scale today, but it represents exactly the kind of workaround that keeps showing up across multiple different corners of Chinese semiconductor research this year, finding ways to achieve frontier-level results without needing the exact tools export controls were designed to keep out of reach. As exciting as this result is, it's worth being clear-eyed about the distance between a published research paper and something running inside a commercial AI data center. This system needs to be tested at genuinely large scale, connecting not just a handful of chips in a controlled lab environment, but potentially thousands of chips working together the way real production AI clusters actually operate, where reliability and consistency under sustained heavy load matter enormously. It needs manufacturing processes that can produce these optical interconnect components reliably and affordably at the volumes a real data center would require, since a component that works beautifully as a handful of research prototypes does not automatically translate into something that can be manufactured by the millions at a reasonable cost. It needs integration with existing data center infrastructure, cooling systems, and software stacks that were built around conventional electrical chip-to-chip communication, rather than optical links. And, like most breakthrough research results, it needs independent replication by other research groups outside Peking University, the standard process through which the broader scientific and engineering community confirms that extraordinary results hold up under further scrutiny.
None of these hurdles diminish what was actually demonstrated here. They simply mark the usual, necessary distance between an important, peer-reviewed paper and a technology sitting inside the data centers actually training and running the AI systems the world uses every day.
So here's the real question worth sitting with. For years, the AI industry's answer to almost every scaling challenge has been the same. Build bigger data centers, buy more chips, spend more on electricity. What happens to that entire calculus if the actual bottleneck was never the chips themselves, but simply how slowly they were talking to each other? And that problem turns out to be solvable with something as old and simple as a beam of light. Let me know what you think in the comments. And if you want more grounded breakdowns of the real engineering breakthroughs reshaping how AI systems actually get built, subscribe, because this optical interconnect story is very likely just getting started.